Okay, welcome AP Chemistry students. This is a brief um, web video on sections 2.1 and 2.2 in your AP Chemistry text Zumdahl, highlighting just really the early history of chemistry and the fundamental laws of chemistry. So after viewing this lesson, you should be able to explain how the scientific process in terms of matter has evolved, be able to explain the law of conservation of mass or the law of conservation of matter, and who are the scientists that contributed to that work, as well as defining the law of of definite proportions and the law of multiple proportions, as well as the scientists who helped develop those laws as well, which are known as the fundamental laws. Okay, in ancient times, science has always been important. Knowing what matter is made up of has always been a human endeavor to understand. In the ancient times, there were the Greeks who believed that really everything was made up of either earth, air, fire, or water. And Greeks actually came up with the first word atom. They did not do a lot of experimentation, though. It was more based on a philosophy. As humans have developed, though, and in the 1500s, 1400s, there was a group of scientists or group of people that were alchemists, and their attempt was to do work, either scientific or otherwise, to change cheap materials into gold was one thing. In the Eastern civilizations, it was to develop the elixir of life, the Holy Grail, the potion that would cause an emperor to live forever. And with this type of work, there was some good things that had happened. There's actually lots of laboratory procedures that were written down. So starting to write recipes, if you will. Also the development of glassware and some unique glassware that we use today as far as a chemist kind of was birthed out of alchemy. So alchemy was basically more of an art or a trade, and from that, chemistry was developed. This picture here is a picture of actually Bronte, and I believe that you watched him in the video. Hopefully you watched the video, The Mysteries of Matter, the first portion of that, where they talk about him moving into the alchemy piece of it and being able to discover phosphorus. Again, here on the lower right is another laboratory picture of what those early alchemist laboratories looked like. In the 17th century, so we're talking 1600s, Robert Boyle was the first to actually perform quantitative experiments. So he's defined as the first chemist. He was more interested in, writing down what he observed and then trying to make sense of what he observed, compared to, the idea of arguing about it based on logical rules by Aristotle. So prior to the 17th century, actually experimentation was considered to be very controversial, and everything was done more based on the Greek ideas. So Robert Boyle, first chemist, first to perform quantitative experiments, and remember, quantitative meaning that it has to do with numbers. Okay, he wrote down his work, he published his work, and that also was a big deal, to be able to publish the work and expect other scientists to be able to confirm the work that you did. This again, too, I don't know if I had said it, but this is Robert Boyle, who had done his work first with pressure-volume relationships with gas in the 17th century. And then as we move towards the 18th century, there's really that idea of understanding what's happening in combustion. Scientists really were fascinated by the idea of burning and what is actually happening in burning. And this brings up a point that there can be a theory for many years, actually centuries, and they can be wrong. And that's the case of this phlogiston theory, proposed by a guy by the name of George Stahl. He believed that there was things that would flow out of burning material, which, because they were kind of playing around with masses and they were starting this idea of, well, trying to understand that idea of conservation of mass, but they were having some difficulties with masses not lining up right. So one of the experiments was actually, or thoughts was actually, there was this mysterious material that you could not see called phlogiston, which would flow out of material or it could flow into material. And it's actually a wrong. In today's term, we now know that phlogiston theory is not correct. But it's interesting to note that for hundreds of years, people believed that that was the current theory. A guy by the name of George Priestley, who was an Englishman, and Anton Lavoisier actually discover oxygen gas in the 18th century. And they did this actually in the video that you watched with The Mystery of Matters. It did talk about Priestley and Lavoisier. And Priestley was a little bit more observational in his work. He was actually a scientist who had done a lot of work with different gases. He was the first to actually, as you saw in the video, do carbonation, understand CO2, carbonated water, with that brewery example. And Lavoisier was a Frenchman who was very established. He was rich. He had the money and the means to develop a very expensive laboratory, and that is what he is known for. His laboratory methods were so good because he's painstakingly measured out matter very precisely. And here in Anton Lavoisier's in the 18th century, he's really defined as the modern quantitative chemist. He disproved the phlogiston theory by heating materials in a closed container, so it was more controlled, and there wasn't an increase in mass because of the oxygen from that. So what had happened with this is that they discovered oxygen. Actually, Lavoisier gets the credit for the discovery of oxygen because of his quantitative methods. And also, Lavoisier then states the law of conservation of mass that says that matter cannot be created nor destroyed. So what does that mean? That means whenever you take a certain amount of one element, let's say you take 32 grams of sulfur and you're reacting 56 grams of iron, you're going to, and you heat it in a controlled experiment, you are going to produce 88 grams of iron sulfide, okay? This work was verified by Lavoisier with his laboratory tools at the time. All right, there's early then in the 19th century, so we're talking early 1800s, the law of definite proportions was written by a guy by the name of Joseph Proust. He said that a given compound always contains exactly the same portion of element by mass. So what that means, and it's almost intuitive today, that if we're talking about a compound, say like carbon tetrachloride's chemical formula is CCl4. So that means there's one atom of carbon for every 4 atoms of chlorine. And he proved this experiment again by masses. And this slide here illustrates that if we had 10 grams of lead and 1.55 grams of sulfur, you will make 11.55 grams of lead sulfide. If you had 10 grams of lead and 3 grams of sulfur, you're still only going to make 11.55 grams of lead sulfide, and you're going to have excess sulfur. That is because there is a ratio that will follow this law of definite proportions of how much lead to how much sulfur you can have in that compound of lead sulfide. And finally, the last law that we're going to talk about today is the law of multiple proportions, written by John Dalton in about the mid-19th century, so mid-1800s. And what he really discovered was that when two elements form two different compounds, the mass ratio of one compound is related to the mass ratio of the second. And again, this isn't really anything that's earth-shattering today, but remember this work was being done in the mid-1800s, where it was very difficult to get really good masses. You had to have a very expensive balance. You had to have controlled experiments. This work was very difficult to do in the mid-1800s. What he is saying is that if you take the mass of oxygen over the mass of carbon in a carbon-oxygen mixture, you could end up with a ratio of 2.67, twice as much oxygen as you have carbon. That would be the compound CO2. If you mixed carbon and oxygen in a low oxygen environment, you're going to produce carbon monoxide, which is a 1-to-1 ratio between carbon and oxygen, and the mass proves that as well. 16 grams of carbon to 12 grams, or excuse me, 16 grams of oxygen to 12 grams of carbon produces a 1.33 ratio. Looking at these two ratios, you'll notice that it produces a small whole number. That's what the law of multiple proportions indicates. It basically is telling you that when you combine two elements together, you can have different compounds, but they're always going to be related by a small whole number. In your textbook, I'd like for you guys to take a look at example 2.1 because this is an example that illustrates the law of multiple proportions. And frankly, I've seen this as multiple choice questions on the AP exam. Here you'll notice that you have some data. You have compound A, B, and C. And it says the following data were collected for several compounds of nitrogen and oxygen. Show how this data illustrates the law of multiple proportions. Well, to do that, it's relatively simple. All that you have to do is you just need to take a look at ratioing the different weights that you have here of your compound, and you'll notice that you get small whole number ratios, which results in the support of the law of multiple proportions. All right, so this is the end of the tutorial on section 2.1 and 2.2. You should be prepared in class next time we are together. You will be working within your table groups and you will be working with this information to be able to discuss as a group questions regarding this video. Good luck and have a great day.